Okay, so now we know about the fundamental data types available in C++. We know how to declare and initialize local automatic variables of these types. We've taken a look at arithmetic, and we've told you and warned you about the integer promotions and the standard arithmetic conversions that occur on a sub-expression by sub-expression basis. It's very important to keep track of that when you're doing any kind of arithmetic computation. Here in Lecture 3, we're going to take a look at assigning new values to variables. We're going to also talk about making decisions and the equality, relational, and logical operators that C++ provides. To improve our ability to process input from the user, and also just in general to keep track of string values, we're going to discuss the string library class type. Okay, so near the end of the previous lecture, I showed you an example of using the cin standard input stream object with the extract or get from operator to read data into a variable of some type. And that construction has a lot of problems in terms of handling errors because users make every error you can imagine and a lot you can't imagine. So what we're going to do instead of using the cin with the get from or extract operator is to use the getLine function to read text from the standard input stream object into a string object. Now, string, as I said, is one of the C++ standard library classes. In order to use string, you have to include the string header. And getLine is a standard library function that knows how to read a sequence of characters that the user types from the standard input stream and put that sequence of characters into a string object. All right, so here we are including string. We are saying that S is an object whose data type is string. Now, I made an issue in the previous lecture about always initializing variables whenever you can. It turns out that string objects, by default, are empty strings rather than random garbage such as an int or a double that was uninitialized. Okay, so S is initialized as an empty string, and now I can call getLine to read whatever the user types in up to the enter key, and that will be stored into the string variable S. Once we've used getLine to read a string into some string object, we then need to analyze whatever it is that the user typed. And in order to do that, we're going to need a bunch of additional mechanisms. We're going to need to be able to do assignment of values to variables. We're going to need to make decisions about whether what the user typed was valid or not. We're going to, in order to make decisions, be able to do equality and relational and logical comparisons. We're going to need to be able to find out how long a string is. We're going to need to be able to convert from a string into a floating point value and a bunch of other things. Okay, so first of all, assignment. In this example here, I'm declaring j as an int object, and I'm using the curly brace notation to initialize j to 0. Now, I could have said int j and then an equal sign and a 0, or int j and then parentheses containing 0. You'll see initializations done using various different notations. Here I've just chosen to use the curly brace notation. All right, so j is created and initialized with the value 0. A single equal sign into a variable that already exists, and in this case j exists now because I've declared it and I've initialized it to contain a 0, so j exists. A single equal sign is the assignment operator, and it does the obvious thing. J gets 4, so j started out containing a 0, and now j contains a 4. And as we do in Python, in fact, these were basically borrowed into Python from C and C++, j plus gets 5 is simply an abbreviation for j gets j plus 5. J minus gets 3 is the same as j gets j minus 3. We can use any of the binary arithmetic operators in these so-called assignment operators. In the examples that I showed on slide 4, we started out with an int variable j containing 0, and then the modifications that we made to j all fit into j just fine, because these computations all involved adding an integer, subtracting an integer, multiplying by an integer, etc. into j. But sometimes in your assignment you'll have a large value, such as a double, that you need to store into a small variable, such as an int. And when you take a large value and store that into a smaller variable, what's called narrowing takes place. And the details of narrowing will depend on the data type of the object you're assigning into and the data type of the value that you're assigning from. For example, here, j is an int object, and I'm assigning a double value into j. Now, 5.6789 will certainly fit in the range of values that can fit into j. J can contain integer values roughly between plus and minus 2 billion. But of course, an int cannot contain a fraction. So what happens is that the fraction part is truncated, and j ends up getting 5 as a result of that assignment. Now, here in the next statement, we have a value that's far larger than 2 billion, 10 to the 30th power. That is way outside the range of things that can possibly fit into an int on our system. And so the result of this is going to be undefined. If we display j after we do that assignment, something will be displayed, but we have no way of predicting what. Also, I want to warn you that you're unlikely to get a complaint from the program as it's running. C++ is a language that's basically obsessed with speed and leaves it up to you, the programmer, to do things that make sense. If you try to do something that doesn't make sense, the compiler in the runtime environment may not tell you that anything is wrong. It will just charge ahead, blindly following its promotion and conversion and narrowing rules, and you get what you get. Okay, continuing on. Here, C is declared as a char, so C is able to contain any value in the system's character set. We know that the 7-bit ASCII character set will fit into C. I'm trying here to initialize C with a double precision value, a floating point number. A char is a subset of the integer data types, and it can't contain a fraction. So again, what happens is that the fraction part is truncated. What ends up happening is that the decimal value 49 is stored into the variable C. And if I look up what that decimal value 49 corresponds to in my ASCII table, I'll see that that's character 1. Let's have a quick look at that. All right, so here's decimal 49. And if I assign the decimal value 49 into a char, that's fine. If I then display C using cout with the put2 operator, what will appear on my screen is the character 1. Okay, now, since a char is one of the integer data types, I can say C times gets 2. This is equivalent to saying C gets C times 2. When I compute C times 2, the char value of C, 49, is promoted to int. I end up doing an integer 49 times the integer 2, which computes an integer value 98. When the integer value is assigned into C, that is, the int value is assigned into C, that does a narrowing, but the narrowing preserves the value, because that value 98 will fit within the range between 0 and 127, which we know any character is able to contain. All right, now if we look up in our ASCII character table what 98 corresponds to, we'll discover that the decimal 98 corresponds to the letter lowercase b. So if I now were to display the value of c, what would be displayed on my screen is a lowercase b. This value, 5432, is outside of the range of values that we know will fit. We know that the values between 0 and 127 will fit. Now, if my particular compiler implements char as an unsigned type, then in my particular compiler, I can store values between 0 and 255, but this value, 5432, is far outside of the range from 0 to 255. Similarly, if char is a signed data type in my compiler, then the range of values that can fit are between minus 128 and 127, and 5432 is still outside the range that will fit. So some pattern of bits will be assigned into this variable c, but the specific result of that is undefined by the language. It will be consistent for your compiler, it will be consistent from run to run for your compiler, but it may be different from what you get from some other compiler. Okay, so as a quick demonstration of the narrowing that's going on in these examples on slide 5, I've written a quick little program, narrow.cpp, in my Ubuntu terminal, which has the declaration and initialization of J and C, and then these assignments to J and C, with cout statements that's displaying what's going on with these things as J and C change. So let me save this and quit from the editor, :WQ. Let me just display the file to confirm that it contains what I want. All right, looks good. Now let me compile this thing. I want the name of the program, the executable program, to be narrow, and narrow.cpp is the code file. Now, my GNU C++ compiler is smart enough to warn me about a couple of overflow problems with this huge floating point number assigned into this int variable j, and this large integer value, well, relatively speaking, large integer value assigned into this character c. Your compiler may or may not warn you, but notice that these are only warnings, they're not errors. So the program was compiled successfully, and I can now execute the program. Okay, and so j was initialized as an int containing 0. When I said j gets 5.6789, as I claimed, what got stored into j was actually the int value 5, because the fraction was truncated. When I assigned this large double precision value into j, I got some kind of undefined result, which happens on this system to be 2,147,483,647. I might get different results on a different compiler or whatever. When I declared the char variable c and initialized that with the double value 49.7, the fraction got truncated, and 49, if it's displayed as a char, all right, here c is a char, and when I display c as a char, what I get is the character 1. If I double c, then c becomes 98 as an integer, but if I display 98 as a character, what I get, as I saw, was the little b. And then finally, when I store 5432 into c and display c as a character, what I'm getting is character 8. All right, so evidently the integer value of c is equivalent to 56, I would guess. 48 plus 8 would be 56. Okay, so that's what's going on with narrowing. Okay, so there we saw some examples of int and char objects having floating point numbers or integer values assigned to them. On slide 6, we're doing this with bool values. It turns out that assignment of any kind of 0, whether it's an int 0 or a floating point 0.0, any value of 0 assigned into a bool variable will cause that bool variable to be false. Any value other than 0 will be true. Okay, so in this first statement on slide 6, I'm declaring that b1 is a bool object, and I'm initializing b1 to true. I am using the equal sign, but because this is the statement in which the variable is being declared, technically this is not an assignment operation. This is an initialization operation. In the second statement, I'm declaring a bool variable b2, and in this case I'm using the curly brace notation to initialize b2 to a 123 rather than the equal sign. Now 123, of course, is not true and not false, but because it's non-zero, the effect is that b2 is going to be initialized with the value true. If I assign the integer value 0 into b1, that's equivalent to assigning false to b1. On the other hand, if I assign the character code for the character 0 to b2, well, the character code for the character 0 is 48. Okay, here's the character 0, and its character code is 48. 48 is not 0. So the upshot is that b2 has the value true assigned to it. In the next statement, this double precision value is enormous in size, and so we discovered when we tried to assign something like that to an int that we got an undefined result because it was too big to fit in the range from plus or minus 2 billion. But here, all that we care about is, is that value equivalent to 0 or not? It's not equivalent to 0, and so b1 has the value true assigned to it in that case. I also just noticed this statement is missing its semicolon at the end. There needs to be a semicolon there after the 30. If I say b2 gets double precision 0.0, well, b2 gets false. And the null character, which is usually written as quote \0 quote, the null character is the character whose character code value is 0. Okay, so this is another way of assigning 0 that is false into b1. Okay, so 0, 0.0, quote \0 quote, all have the value 0. In one case we have an int value 0. In another case we have a double value 0. And in the third case we have a char value 0. But regardless of what data type that 0 is, when we assign the 0 to a bool, that bool is going to contain the value false. All right, now the simplest form of decision that the C++ language provides is, surprise, surprise, if. It's very similar to if in other languages. The idea is that you have some expression. In the C++ notation's case, the expression has to be contained within parentheses characters. And if that expression evaluates to true, that is, if that expression evaluates to anything that's not 0, then the statement within the body of the if decision is going to be executed. Otherwise, we'll simply skip over that statement and go on to whatever statement follows. Now, the statement here within the body of the if can be a single simple statement ending with a semicolon, or it could be a compound statement contained in curly braces. So you can put curly braces around some sequence of statements to create this thing called a compound statement. And having a compound statement enables you to put multiple statements into the body of the if. Here we have a few examples on slide 8. So I is an int initialized with the value 12. Since the value of I is greater than 6, notice my required parentheses to contain the test expression in C++. Since the value of I is greater than 6, I'm going to invoke this cout simple statement displaying that I is greater than 6 and a new line. If I is less than 6, well, that's false, so I'm going to skip over this blue cout statement, and nothing is displayed for this blue test, this blue if decision. In the red test down here, we're just saying if I. Now, this is equivalent to saying if I is not equal to 0. Because 0 is treated as false, anything other than 0 is treated as true. So if I is not equal to 0, and clearly 12 is not equal to 0, so I is equivalent to true, perform this compound statement consisting of both of these two cout statements within this curly brace pair. We're going to display that I is 12, and we're going to display non-zero is true. And we have a new line character here, and we also have a new line as part of this double-quoted string down there. So that's the if decision. If very often has an else clause attached to it, and the behavior here is straightforward. If the test expression between the parentheses is true, then statement 1, which may be a simple statement or a compound statement, is executed. Otherwise, if the expression here is false, statement 2 in the else will be executed. And again, statement 2 may be a simple statement, or it may be a compound statement contained within curly braces. For notational reasons, until you're pretty good with C++, I'm going to suggest that you go ahead and use compound statements both for the if part and for the else part. It's much easier to do debugging and to read code if you always use compound statements, even if the body of your if is only a single statement long. That is, over here on slide 8, we said if I is greater than 6, and then we had a single simple statement in the body of the if. I would recommend, as a practice until you get to be very skilled with C++, put your curly braces in here anyway, even though there's only one statement in this if decision. Okay? Put an opening curly brace after the closing parenthesis, and put a closing curly brace below that statement that you want to have within the if. For one thing, if you then come along later and add another statement in your if, well, that will work because then you have another statement within that compound statement. Otherwise, if you try to add another statement but you forgot your curly braces, you'll probably end up getting a syntax error because you're attempting to have two simple statements as the body of an if, and that will be an error unless you have curly braces around both simple statements. Okay, so here we have an example, a couple of examples of an if-else. I is initially 12, so I is an int variable initialized to 12. And we're saying if I is greater than 12, well, that's false. Well, that's false. I is not greater than 12, so we skip the statement in the if part, and we come down to the statement in the else part and display I is less than or equal to 12 with a new line. If I, as I said, is equivalent to saying if I is not equal to 0. Well, at this point, 12 certainly is not equal to 0. That means that we execute the statement within the if rather than the else. And notice what's happening here. We're going to execute this statement that's within the if. I is 12. But this next statement down here, even though I've used indentation as I would in Python, is not actually within the body of that if. This is a separate statement, not contained within the body of the if. And in fact, when I then get down, well, when the compiler gets down to this else word, the compiler is going to say, hey, wait a minute, you have an else here, but this else is following this C out. I don't see any if corresponding to this else. So the bottom line here is that indentation means absolutely nothing to C++. Remember that C++ is a free format language. If I want both of these statements to be controlled by this if test, I must put curly braces to contain those two cout statements. Otherwise, I have a syntax error. Okay, so remember, as I said, that C++ is a free format language. Indentation does not mean anything. Indentation is merely used to try to make the code look clean and tidy to other programmers reading your code. Here is a typical chain of if-else statements. Notice that C++ does not have a separate keyword elif, the way that Python does. In C++, all we have are if and else. But we can accomplish else if quite easily. We say if this test is true, then do this compound statement. Else, if this test is true, then do this compound statement. And notice that in each case, these compound statements only contain a single simple statement, but that's fine. Else, if this test is true, do this compound statement. And finally, else, do this compound statement. All right, so I recommend structuring your if-elses in this way, always using curly braces to contain whatever is supposed to be controlled by the if or the else. Getting in that habit will save you from a lot of aggravation and complaints from your compiler. All right, well, I've used the less than sign in a whole bunch of these examples, just assuming that you knew what it meant, which you did. Here is the complete collection of equality, relational, and logical operators in C++. These are quite similar to what we had in Python, except that the precedence rules are quite different. And we have symbols rather than words for the three logical operators. So for logical not, we have exclamation mark. For logical and, we have two ampersand symbols. And for logical or, we have two vertical bar symbols. Notice that the not has the very highest precedence of all of these operators. And notice also that the relational operators, less than or equal, greater than or greater or equal, have higher precedence than the equality and inequality tests. All of these operators produce a result of either true or false. And as you would assume, you can use parentheses if you want to override or clarify the precedence by which you want the expressions to be evaluated. These precedence rules are intended to mimic how you think about logical comparisons when you're saying them aloud. For example, if I have this fairly long-looking test, I'm asking whether A is less than B and C is greater than D, or not E is equal to F and G is greater than or equal to H. Now, that's a long expression, but I hope that the way I pronounced that did not sound peculiar. I hope that that sounded like a natural way of pronouncing this thing. And if you listen back through what I said, it did sound like the or had the lowest precedence. I said, is A less than B and C greater than D, or is not E equal to F and G greater than or equal to H? So the or does have the lowest precedence, and it sounds like it has the lowest precedence. Then the ands have the next higher precedence. Okay, we're asking whether A is less than B and C is greater than D. Then we're asking whether not E is equal to F and G is greater than or equal to H. I can put in all of the parentheses corresponding to these precedence rules on slide 12. It's not clear to me, though, that adding all these nested parentheses helps make this decision more clear. Sometimes you'll discover that just writing your test down in a natural way, assuming that the precedence rules make sense as they would in an English sentence, gives you something that's more readily understood than if you actually put in all of these nested parentheses. Well, that's up to you. But nevertheless, these are the rules. You will unfortunately need to know these rules, and the precedence rules are unfortunately not the same as they are in Python. Now, like in Python, the logical operators in C++ provide short-circuit evaluation. That is, evaluation of these is always from left to right, and as soon as we can figure out the overall truth or falsity of the entire sequence of expressions, we stop evaluating any further parts. For example, here when I'm using an AND, if we immediately discover that expression 1 is false, we don't bother to evaluate expression true because false and anything is false. All right, so false implies that the whole thing is false, and consequently we skip this statement. On the other hand, with OR, if we discover that the first expression is true, there's no point evaluating the second expression because true or anything is going to be true. All right, so if we discover that expression 1 is true, we just immediately evaluate the statement within the if. We don't bother to go on and evaluate expression 2 at all.